entropy. Entropy is a very fundamental principle in physics and is equal to the amount of disorder in a system. Entropy always increases in a natural process. And the equation for entropy that defines entropy is given here. Entropy, S, is equal to Boltzmann's constant times the natural log of omega, where omega is the number of possible states a system can be in. Now, we actually won't be using this equation in this class. It's actually a very difficult equation to use because finding omega for any given situation is quite a lot of work. In fact, there is an entire upper division physics course called Thermodynamics and Statistical Mechanics, where we spend a large portion of the class learning how to calculate omega for different systems. Instead, we'll be looking at a simpler equation involving finding the entropy, which we'll see later on. Now, entropy always increases in natural processes because more disordered systems are a lot more likely than ordered systems, and this is because there are a greater number of them. So, to take a very simple example, think about flipping a coin 3 times. This table gives a list of all of the possible outcomes. You could have 3 heads, you could have 2 heads and then a head and then a tail and then a head, or a tail and then 2 heads. You could also have 1 head and 2 tails, and there are 3 ways of accomplishing that, and then you could have 3 tails. If you look at the number of ways there are to get each of these outcomes, you can calculate the probabilities. So the probability is 1/8 that you get 3 heads, because there's 1 way to get 3 heads, and there's 1, 2, 3, 4, 5, 6, 7, 8 total different outcomes. On the other hand, there are 3 ways to get 2 heads and a tail, so the probability of getting that outcome is 3/8. So since there are more ways to get 2 of a kind instead of all the same kind, it's more probable, and these more disordered options have higher entropy, simply because there's more ways in which they can occur. To take another example, think about having particles in a box. Now let's say you label the particles 1, 2, 3, and 4. There are a total of 24 ways the 4 particles can be in the 4 different quadrants of the box. So if we split the box up into 4 different parts, so we're just drawing imaginary lines here on the bottom of the box and seeing where the particles end up. If we have each particle in 1 quadrant of the box, there's 24 ways that can happen. You can have 1, 2, 3, 4, you can have 1, 3, 2, 4, 1, 4, 3, 2, and 1, 2, 4, 3, and that's just 4 possibilities. There's a total of 24 ways that you can distribute these 4 particles. However, there's only 1 way that all 4 particles can be in 1 quadrant. That's just that they're all in the 1 quadrant. And so if you were to put particles in a box, if you were to just chuck the particles in and then looked at where they landed, you would much more likely find that they're spread out in the box than all in one place, since there's more ways that that can happen. And that's why you're never going to walk into a room, step through the door, and pass out because the part of the room that you are in contains no air. No, the air molecules are going to be spread uniformly throughout the room, not all in one corner, because there's many more ways that they can be distributed around the room than all in one place. So since that more disordered way of the particles existing is more likely, that's what you're always going to find when you walk into a room. Same thing if you take a bag of M&Ms and dump it on the table. You'd be mighty surprised if all the colors ended up sorted in that pile. No, they're all going to be mixed together because there's way more ways that they can be mixed together than sorted. So more disorder, higher entropy, that's what occurs, and natural systems always move towards a more disordered, higher entropy state because there's just so many more ways that that can happen. So these more disordered random states are far more likely. The number of disordered states is typically many, many orders of magnitude. You have to write scientific notation with very large exponents in order to express how many more disordered states there are than ordered states, particularly if you're dealing with something like Avogadro's number of atoms. These disordered states have a lot more entropy. So anytime you have a process, the entropy of the universe will increase. A single system's entropy can decrease, but the total will increase. So take our M&M example. You can certainly decrease the disorder of the M&Ms by sorting them into piles. But in order to do that, you're using food energy, and you're taking that energy and transforming it into heat as your muscles are doing work. And so you are creating entropy, and the entropy you are creating is greater than the entropy that is lost by you sorting the M&Ms into piles. So work always goes from a more to a less usable form as heat carries the energy away and distributes it among different particles. And this has led to something that a concept that scientists term heat death, which says, according to physics, as entropy increases, with every process, the entropy of the universe increases, and eventually everything in the universe will run down. If you look at a star like our sun converts hydrogen into helium. It does this nuclear fusion process, and it generates energy, it generates light and heat, and that spreads out throughout the universe. So the sun burns hydrogen and turns it into helium. And when it runs out of hydrogen in its core, then it will start fusing helium. And it will go to heavier and heavier elements until it gets to iron. Then you can't fuse iron. Iron doesn't fuse. To combine with something else requires an input of energy, and it doesn't release energy. And so when the sun, as it converts heavier and heavier elements, the sun actually won't get all the way to iron. Heavier stars are able to do that, but it will get to about carbon and then not be heavy enough to fuse carbon. And so it will eventually, the sun will start to swell and then it will fizzle. And all of the stars in the galaxy will eventually go through this process. You can create new stars with some of the gas and dust that's out there, but eventually that gas and dust will get used up in stars, and then the stars will run down, and then everything will run down, and eventually all of the stars will die, and all of the energy in the universe will be evenly distributed throughout the universe in a soup, and everything will be cold and dark and dead. So I like to call the heat death of the universe the ultimate answer to the very first lie. If you think back, what was the very first lie? The serpent told Eve, "You shall not surely die." Well, the entropy, the physics says, yes, everything in the universe without divine intervention will surely die. It will all die. Everything will succumb to the heat death eventually. Although that eventually is a very, very, very long way away. So the sun has about 5 to 6 billion years of fuel left. So this is not a today sort of problem, but it is an ultimate answer to the very first lie. So the equation that we will be using when we talk about entropy is we will be looking at entropy, or the increases or decreases in entropy of a system when the temperature of that system remains constant. So if you have an isothermal process, then you can calculate the change in entropy of that process using this expression. So it's the heat that enters or leaves the system divided by that system's temperature. And this is a nice equation. It only depends on the endpoints of the process. And this equation too gives us an idea, or contains the idea, of why we can't have a perfect heat engine. We can't have a perfect heat engine because heat always carries entropy. So if you have heat entering the heat engine, so QH, heat enters the heat engine from the hot reservoir, it carries entropy with it. And so you have to have heat leaving the engine in the form of QH to carry that entropy out of the heat engine. If you don't have waste heat, then entropy would build up inside the engine and eventually the engine wouldn't be able to function anymore. Work does not transmit entropy like heat does. So if you have heat entering the engine, you also have to have waste heat leaving the engine in order to carry that entropy with it. So the Carnot engine is the ultimate efficiency engine because it doesn't generate extra entropy. It just takes the heat that comes in, carries some entropy in, and that same amount of entropy is exhausted in the heat transferred to the cold reservoir, but the Carnot engine does not create any extra entropy within itself. Real engines do create a little bit of extra entropy and so need extra heat leaving and are less efficient in order to carry that entropy out of the engine. So let's next take a look at this example problem. We have a cylinder containing an ideal gas that has a volume of 2 cubic meters and a pressure of 1 × 10⁵ pascals at a temperature of 300 Kelvin. The cylinder is placed against a metal block that is maintained at 900 Kelvin, and the gas expands as the pressure remains constant until the temperature of the gas also reaches 900 Kelvin. The change in internal energy of the gas is 6 × 10⁵ joules. Find the change in entropy of the block. This problem sounds awfully familiar. This sounds like one of the very first problems that we looked at during this lesson. So if we remember when this problem was posed before, we had all the same numbers and we were just asked to find the heat that entered the gas. And this heat would be coming out of the block and going into the gas. So we already know the heat that the block gives to the gas. And so we can use that then to find the entropy. So if we look at this problem, we have our cylinder. We have our cylinder of gas, and it's resting on this block, and the block is maintained. The temperature of the block is 900 Kelvin. And we know that heat goes from the block into the gas. And we're asked to find the change in entropy of the block. So we know that the change in entropy, and this is going to be the change in entropy of the block, is the heat exchange for the block divided by the temperature of the block, since we're looking for the change in entropy of the block. So we know that the block always maintains 900 Kelvin, so that is the constant temperature that we would use, and then the heat exchange for the block, well, we found that in the last problem. We saw that there was 1 × 10⁶ joules going from the block into the gas. And so the heat exchange for the block would be minus 1 × 10⁶ joules, because that much energy is leaving the block. So we have a negative. So the entropy change for the block would be negative 1.11 times 10⁵ joules per Kelvin. So this would be the entropy difference, the amount of entropy that the block loses. It's because we remember that heat always carries entropy with it. So if heat is leaving the block, then entropy will be leaving the block along with the heat. So entropy change for the block is negative, and that's okay. The block can lose entropy as long as the gas gains just as much, if not more, entropy than the block loses.